Today we're going to talk about work done by a constant force. So we all use the word work already in our lives, so what I'd like you to do is put in a definition of the word work, and that can be just however you use it, an example of work being done. And our essential question for today is, how do you calculate the work done by a force on an object? I'd like to think about some situations where I'm doing work by my arms. So what if I push on the wall real hard for 30 seconds? Or maybe if I carry my book across the room, or maybe I just lift the book from my chest to my head. In which one of these situations do you predict that my arms will do the most work? Next, I'd like you to do a little research on work and look in your textbook. So if you have the AP textbook, that's the book that has like the 4 pictures on the front. You'll do pages 164 and 165. If you're in the old AP textbook, it has like that starburst thing on it. So then in that, you'll read 155 and 156. And if you're in the mechanics book, that's the book with the mountains on the front. And you'll read pages 137 and 138. And what I'd like you to do is just put 4 new things in your notes and then give those on this page as well. So some things from the reading that I thought were important is that the definition of work is defined as a force times a displacement. The force has to have some component in the direction of the displacement. Notice that there has to be a displacement. If the object does not move, then no work is done. Our equation for work is FD cosine theta, and we'll talk more about this cosine theta piece later, but the main idea is that it's the force times the displacement, and then the force needs to be in the same direction as the displacement. The unit for work is the joule, which is equal to 1 Newton times a meter, and we can talk about work being done on an object or work being done by an object. So let's look at those situations where we talked about work being done by my arms. So if I'm standing here and push on the wall for 30 seconds, how much work was done? Well, again, work is FD cosine theta. And the displacement in this case is 0. So there was actually no work done there. When I carried the books across the floor, again, our work equation, work equals FD cosine theta. My force, I did have a force on the book that was up. There was a displacement, which is in this direction, but the angle between the force and the displacement was 90 degrees, and cosine 90 is 0. So in that case, no work was done. When I lifted the book, now I lift the book from my chest height and I lift it up. Now in this case, the force is up, the displacement is up. So when I do work equals FD cosine theta, there was a force in this case, there's a displacement in this case, and the angle between the force and displacement is 0 degrees because they're in the same direction, and cosine 0 is 1. So only in the case where I lifted the book did I do any work. So let's look at an example where I need some help moving my desk. So here's my desk, and I want to push it in this direction. So I stand back here and I'm pushing on my desk. And student A comes up and they want to help out. So they start to push this way. And my desk slides along in this direction. And after it goes, that student sits down. And I thank them because they helped out. But really in my head, I'm thinking, okay, work equals FD cosine theta. The student did a force and the desk did move, but the angle between the student's force and the displacement is 90 degrees, and the cosine of 90 degrees is 0. So in my head, I'm thinking, thanks, but you really didn't do anything. So then let's look at a second situation where I'm trying to push my desk, and a student comes up to help, and I'm pushing my desk, and the displacement's in this direction, and a student pushes this way. So again, in my head, I'm thinking work equals FD cosine theta. Well, the student did apply a force, and there was a displacement, but the angle between the force and displacement now is 180 degrees. In this case, cosine 180 is -1. So in my head, I'm thinking, not only did you not help, you did negative work. So what if I have a third situation where I have my desk, and I'm pushing my desk with a force, and it goes in this direction, and the student comes up and pushes this way. So now I have to calculate the work done to know how much they helped me. FD cosine theta. Well, the person did apply a force. There was a displacement. And now there is an angle between force and displacement, so I could get the value of that. So in this case, there was work done. So it doesn't have to be all in the direction, but as long as there's some component of the force in that direction, then work is done. So here's a sample problem. A box is being pulled along flat ground. So we have a box, flat ground, and it's being pulled by a rope, and there's 100 newtons of force, and it goes 20 meters, and it says that the angle between the force and the horizontal, which is the way that it's going to go, is 60 degrees. And it says how much work was done by the rope on the box. So we can use our equation, work equals FD cosine theta. Work equals the amount of force on the box was 100 newtons, displacement 20 meters, cosine 60 degrees. So the work done is 100 times 20, and cosine 60 is a half. So the work done is 1,000 joules. What I'd like you to do now is just write down in words, how would you explain to someone else, maybe if someone's not here today to do this, that how would you explain to them how to calculate the work being done? One of the most common questions that I got when I do this lesson is about this 180 degrees. You can see that a number of students have asked about this. The reason why we use 180 is, again, let's say I'm pushing a box in this direction. Well, the friction force goes in the opposite direction. So when we look at this, since it moves to the right, that angle would be 180 degrees. And again, if you remember from pre-calc or wherever, that cosine 180 degrees is -1. And that negative sign shows that it does negative work. It actually hurts the motion of the object. Someone else wanted to know, what is it called when you exert a lot of force on the wall if it isn't work? And that's a good point. Like your arms get tired and things like that. And it's just called applying a force. But physically, there is no work being done since there's no displacement. Someone else who has really nice handwriting, might I add, asked, is work a vector or a scalar? Yeah, I didn't mention that before. But work is a scalar value. If you can't remember what vector and scalar, remember vector is where direction matters. And with scalar, direction doesn't matter. You're not going to have work north or anything like that. You're just going to get an answer like 10 joules of work is done, and that'll be it. Here are some summary questions that you should be answered after we've done this lesson. The one thing we haven't talked about yet is network. And the idea with network is it's the sum of all the works done. So if you're pushing a box to the right with an applied force, then that applied force would do positive work. But if there's friction to the left, again, that whole cosine 180 degrees is a negative, so that does negative work. So if you do positive 10 joules of work, but friction might do negative 8 joules of work, then the net work done is, what's left over after we cancel everything out. So the net work done might only be 2 joules of work.